Hello everyone. In today's world of modern applications, swift responsiveness is essential. Users expect a seamless experience where every action triggers an immediate response. Serverless services such as AWS Lambda allows developers to build modern applications without the need to provision any servers or additional infrastructure. However, these services sometimes introduce or adds a bit of latency when provisioning a new execution environment to run the customer code. This is sometimes referred to as a cold start, and even though production metrics shows that cold starts typically occur for less than 1% of all invocations, and sometimes even less, it can still be a bit disruptive to the seamless user experience that we're targeting. What if I told you that there is a solution to cold starts? What if I told you that you can run JavaScript applications on AWS Lambda with virtually negligible cold starts? So my name is Richard Davison. I work as a partner solution architect, helping partners to modernize their applications on AWS using serverless and container technologies. And I am here to talk about a project that I've been building for some time called LLRT and how it redefines serverless latency. So LLRT is short for Low Latency Runtime, and it's a new JavaScript runtime built from the ground up to address the growing demand for fast and efficient serverless applications. Why should we build a new JavaScript runtime? So JavaScript is one of the most popular ways of building and running serverless applications. It also often offers full stack consistency, meaning that your application backend and frontend can share a unified language, which is an added benefit. JavaScript also offers a rich package ecosystem and a large community that can help accelerate the development of your applications. Furthermore, JavaScript is recognized as being rather user-friendly in nature, making it easy to learn, easy to read, and easy to write. It is also an open standard known as ECMAScript, which has been implemented by different engines, which is something that we will discuss later in this presentation. So how is LLRT different from Node, Bun, or Deno? And what justifies the introduction of another JavaScript runtime in light of these existing alternatives? So Node, Bun, and Deno, they represent highly proficient JavaScript runtimes. They are extremely capable and they are very performant. However, they're designed with general purpose applications in mind. And these runtimes were not specifically tailored for the demands of serverless environments, often characterized by short-lived runtime instances with limited resources. They also each depend on a just-in-time compiler, a very sophisticated technological component that allows the JavaScript code to be dynamically compiled and optimized during execution. And while a just-in-time compiler offers substantial long-term performance advantages, it often carries computational and memory overhead, especially when doing so with limited resources. So in contrast, LLRT distinguishes itself by not incorporating a just-in-time compiler, which is a strategic decision that yields two significant advantages. So the first one is that, again, a just-in-time compiler is a notably sophisticated technological component, introducing increased system complexity and contributing substantially to the runtime's overall size. And without a JIT overhead, LLRT conserves both CPU and memory resources that can be more effectively allocated towards executing the code that you run inside of your Lambda function, and thereby reducing application startup times. So again, a just-in-time compiler would offer a long-term substantial performance increase, whereas a lack of a just-in-time compiler can offer startup benefits. LLRT is built from the ground up with a primary focus, performance on AWS Lambda. So it comes with virtually negligible cold starts, And cold start duration is less than 100 milliseconds for a lot of use cases and tasks, even doing AWS SDK v3 calls. It uses a rather recent standard of ECMAScript, so ECMAScript 2020, with many Node.js APIs. And the goal of this is to make it a rather such a simple migration from Node as possible. It comes with what we call batteries included. So LLRT and the binary itself has some AWS v3 SDKs already embedded, so you don't need to ship and provide those, which also has a performance benefit. And speaking of performance benefits, there is also a cost benefit, and more stable performance, mainly due to the lack of a just-in-time compiler, can lead up to 2x performance improvement versus other JavaScript runtimes, and a 2x cost saving, even for warm starts. So what makes this so fast, and what is under the hood? So it uses a different JavaScript engine compared to Deno or Bun. So Deno and Bun uses engines called V8 and JavaScript Core. So V8 comes from Chrome browser and the Chrome team. So the Chrome team has created a JavaScript engine for its browser called V8, whereas Bun uses an engine called JavaScript Core that has diverged from Safari. But QuickJS, on the other hand, is a very lightweight engine. It's very capable, but it's also very lightweight. So the engine itself, when compiled, is less than 1 megabyte. If you compare this with both JavaScript Core and V8, they are over 50 megabytes inside of Node and Bun. So LLRT is also built in Rust using Tokio asynchronous runtime. Many of its APIs that is implemented inside of the runtime are adhering to the Node.js specification and are implemented in Rust. So the whole executable itself is less than 3 megabytes, and that is including the AWS SDK. I think it's time to take a look at a quick demo to see how it performs in action. So here I am inside of the AWS Lambda console. In this example, I have imported the DynamoDB client and the DynamoDB document client to put some event that comes in comes into AWS Lambda to put it on DynamoDB. I also add a randomized ID and stringify the event, and I simply return a status code of 200 and OK. Let's now first execute this using the regular Node.js 20 runtime. And this time we see a cold start. So let's go to the test tab here and hit on the test button. Now it has been executed. And if we examine the execution logs here, we can see that Node.js is executed with a duration of 988 milliseconds and an init duration of 366 milliseconds. So in total, this is somewhere around a little over 1.2, 1.3 seconds, actually. And we consumed almost 88 megabytes of memory while doing so. So what I'm going to do now is go back to the code. I scroll down to runtime settings, click on edit, and change to Amazon Linux 2023, always only runtime. Save it. And now let's execute it with LLRT. As you can see, this was almost instant. And examining the execution logs, we can see that we now have a duration of 29 milliseconds and an init duration of 38, which means that we have a total duration of 69 milliseconds. So 69 milliseconds versus 1,300 or slightly above for Node.js. While doing so, we only consumed about 20 megabytes of memory. And notice that if I run the code again, for warm starts, it's also very fast. We have 45 milliseconds here, 16, 13, 14, 9, etc. So there's also no sacrifice in warm performance, and in fact, it can be up to 2 times less than the Node.js equivalent, mainly due to the fact of the lack of a just-in-time compiler and a simpler engine, so less complexity. Also notice that I didn't change a single line of code. What I simply did was to change the runtime settings here, and I have prepared this demo by putting the LLRT bootstrap binary here. So I simply downloaded LLRT, renamed the binary bootstrap, and put it together with my sample code here. Okay, let's get back to the presentation. So what can be good use cases for LLRT? So good use cases can be latency critical applications, high volume functions, data transformation, integration with different AWS services, and server-side rendered React applications can even be executed with LLRT, and also applications consisting with a lot of glue code. So what I mean by this is that applications that integrates to other third-party sources or AWS, other AWS services, that is the glue between one service to the other. When it's not good to use LLRT is when you're doing simulations or handling hundreds or thousands of iterations in loops, or doing some sort of Monte Carlo simulation, or transferring large objects or large sets of data in tens or even hundreds of megabytes. This is where the just-in-time compiler really shines, which is a feature that is not available in LLRT. So what is best right now is to measure and see, and I'm pretty confident that a lot of your use cases would benefit from running LLRT. And again, how can it be so fast? So it has no JIT, and the AWS SDK is optimized specifically for Lambda. This means that we have removed some of the complexities that involves the AWS SDK, such as we cache object creation, we convert the SDK to QuickJS bytecode, and we're leveraging some other techniques that optimizes for cold starts on Lambda. For instance, we do as much work as possible because the Lambda runtimes have CPU boost when they're being initialized. We also write most of our code in Rust. So in fact, we have a policy that says as much as possible should be written in Rust. So the more code we can move from JavaScript to Rust, there will be a performance benefit. So in contrast with Node.js, almost all of its APIs are written in JavaScript, and they heavily depend on the just-in-time compiler of the V8 engine to achieve great performance. Since we're lacking this capability and writing most of the code in Rust, we get performance benefits while still keeping the size down, and get an instant performance benefit without having to rely on the JIT profiler to optimize the code over longer running tasks. And basically, everything that you use in LLRT is written in Rust. So the console, the timers, crypto, hashing, all of that is written in Rust. There's just a small JavaScript layer on top of that. And of course, your code will be running in JavaScript as well. And it's also, again, very lightweight. It's only a few megabytes. And we try to keep it as lightweight as possible, minimizing dependencies and also minimizing complexity. So what's the catch? So this is a very high-level compatibility matrix. And you can see there's an exclamation mark here, and there's a few check marks. So obviously, there has to be some sort of trade-offs in order to achieve this level of performance. And the trade-offs is that not every Node.js API is supported, but we support some of them. And they're not also fully supported. So even though there's a check mark here, it doesn't mean that it supports, for instance, the full FS module or FS promises module. It's partially supported. But we're constantly building this runtime, and it's available as a beta today that you can check out. And I will have links to it later in this presentation. And how to use it? So like you saw in the demo, I just download the latest release from the GitHub page, which is github.com/awslabs/LLRT. I add the bootstrap executable together with your code. I can also use a layer if that's your thing, or package it as a container image. I then select custom runtime on Amazon Linux 3 inside Lambda as my runtime choice. and LLRT runs on either ARM or x86-64 instances. There's a slight benefit of using ARM because you have a cost savings benefit, and it's also slightly better performance. So this is something that I recommend. Now let's take a look at some benchmark data. So as we saw in the demo, we did a very quick sample where we saw that the cold start benefits and also warm start benefits were significant versus Node.js. This slide here showcases some startup benefits when running on my local machine. So as you can see here in the demo, highlighted by the arrow, that LLRT starts almost 6 times faster than Node.js. This is a pretty unexciting demo where we just do basically a print, but it showcases the lightness of the engine, where it doesn't have to load a lot of resources in order to start. So it can be even faster than Dino and Bun. But bear in mind that a lot of these speeds comes from the simplicity. It's very simple to introduce a new runtime with a limited API and say it's faster. But this is one of the trade-offs, right? So we make it very lightweight, hence it's also naturally faster. Let's now take a quick look at some performance numbers when running LLRT for a longer period of time. So this is again doing a DynamoDB put. So it's the same sample code that we saw in the demo, but however, this is now running for 32,000 invocations on ARM64 with 128 megabytes of memory. So notice here that the P99 latency, meaning that 99% of all invocations are below this number, we have 34 milliseconds for warm starts and 84 milliseconds for cold start. In comparison, we have the fastest possible warm start that is only 5.29 milliseconds and the fastest possible cold start that is 48.85 milliseconds. If you compare this with Node 18, we can see that we have the P99 latency of 164 for warm starts and 1,306 for cold starts for the slowest times, and for the fastest times we have 5.85 and 1,141 milliseconds for a cold starts. This means that there is a 23 times performance improvements for this exact demo for cold starts and a 15-time performance improvement for the worst case. So that this is the best case versus the worst case. Also notice that the number of cold starts that you can see here. So in Lambda, even though cold starts may not be that super critical for your application, so if we can keep them lower, it also means that they are less likely to occur. Because every time Lambda has to process 2 consecutive events and has not done so before, meaning that there are no ready instances, it has to spin up a new one, meaning that you will introduce an additional cold start. So in my example here, we can see that LLRT only introduced 109 cold starts versus Node.js that had 554 cold starts. And again, this is due to the cold starts being much shorter, also less likely to occur in the first place. Also notice here that the duration span of the warm starts, we have 158 milliseconds for the slowest all the way to the fastest invocation for a warm start versus only 29 for P99 with LLRT. And again, this is due to the lack of a just-in-time compiler, making the execution much more consistent. If we take a look at the latency and cost breakdown, we can see that we have a build duration of 22 minutes and 19 seconds for Node.js versus LLRT, we only have 7 minutes and 48 seconds, which translates to a cost saving of 2.9 times and a time saving of 3.7 times. And the reason why these two differs is that it depends on how they're being charged. For provided runtimes is charged a bit differently in Lambda than custom runtimes, but we still have a cost saving of 2.9x for this particular example over 32,000 invocations. And that's it for me. I highly encourage you to test LLRT, so you can follow the QR link here. And please test it out. It's still a very experimental runtime, so do not run it in production just yet, but we're building more capabilities every day. And we hope that you provide feedback. And again, I'm Very, very thankful that you took the time to listen to me today, and I hope you enjoy the rest of Node Congress. Thank you.